Hello and welcome to Pi Day. I'm going to just start this one with a nice simple method. I thought I'd go back to basic methods of calculating pi. So I've just knocked up a couple of quick functions here which will just do some nice demonstration of how accurate we are. So I pulled down pi from Cambridge University, which has it to like 1,000,000 places or something. And here you can type numbers in here and it will show you quite nicely. If I actually put numbers in, it'll show you quite nicely how accurate your pi calculation is for your input that you put in there, if you actually put numbers in rather than letters. So the first way of calculating pi that I ever discovered was something called the Leibniz formula. The Leibniz formula actually calculates a quarter of pi, so you just multiply that by 4 and you pretty much get there. And the way it works is very straightforward. In that what you're going to do is you're going to count basically a series, and you start off with 1, and you actually start off by minusing 1 over 3, and then you add 1 over 5, and then you minus 1 over 6. Okay, and as that goes on, you end up with a number. So we have quarter pi equals that. So we do pi, or my pi equals 4 times quarter pi. And you end up with a number which is going to be nothing like the actual outcome. Quarter pi, my pi, actual pi. That, and you see it is radically far off. It is massively far. But the further you go down this, so 1 over 6 minus 1 over 7, there's always the odd number. So I'm going to add now 1 over 9 and subtract 1 over 11 and add 1 over 13 and subtract 1 over 15, and you slowly start moving towards pi. So it's now on 3.0. It's still not very good, and it kind of works. It's very easy to sort of work this one out. So what I'm going to do is, as a series, just do quarter pi is equal to 1, and then sine is equal to minus 1, and that's because I want to start by minusing 1/3. So I'm going to do 4I in range, start at 3 and go to 101. Okay, and it's going to basically, and I also want to go up by 2. It's very important because I don't want to go to 5 or 4, so I want to go 3, 5, 7. Okay, and then I'm going to do quarter pi is equal to itself plus the sine times 1 over I. That's straightforward. And then what I'm going to do is I want to flip the sign. So I'm going to do the sine is equal to itself multiplied by minus 1. So minus 1 times minus 1 makes plus 1. Plus 1 times minus 1 goes back to minus 1. So every time that goes round, that should work quite nicely. Right at the end then, I'm going to calculate my pi out. And that gives me an answer of 1.2. So even after 101 digits, I haven't got very accurate. Even after 1,001 digits, still not very accurate. Going up to 1,001, you start getting more accuracy. And the reason for this is that if you look at it at 5 digits in, because to get to 10, I'm only doing every other number, so 5 digits in, I'm still affecting the 10th digit. So if I go all the way up to 1 over 99, this is still going to be affecting the tenths. In fact, 1 over 101, let's go 1 over 101. At that point, I'm affecting the hundredths digit here. So I've actually got to put 50 in before I stop affecting this digit. And because this is a 1, if this was a 1 or 9 here, you're going to be affecting it all the way up to 1,000. So to get up to any number of decimal places, you've got to put quite a lot of digits in before it starts getting any form of accuracy. And in fact, it gets slower and slower because I've got to go tenfold here to get another accuracy. I'm getting 10 times longer to not even calculate. See, it's really taking time to think about it now. But you can see this method is relatively accurate in getting a few digits. You don't need pi to any level of accuracy to do useful maths with. So if you're calculating the area of any decent sized circle, or any volume or any circumferences, you don't really need more than about 3 or 4 decimal places. It's only if you're doing hyper scientific things, or hyper accurate stuff, or very, very large circles, orbits of the planet sort of size. Even calculating like the circumference of the Earth, you don't need that many decimal places. it's actually more, you can get more error from your measurement of the depth and the fact that the Earth isn't circled than you are out of anything else. So this is the method. This is called the Leibniz formula, and it isn't very effective. Like, it is actually relatively slow to get going, as opposed to more clever systems such as which use grills and other things that can calculate using powers and factorials, things like that. But it's easy to understand. I think what's really nice about it is that it's really easy. You can go on and you can work out these ones one by one, and you can sort of pick it up where you go. So when you get to here, you can pick it up and do another million. If I change that to 2, by the way, you'll find that I won't get beyond. I've currently got 926, the last good digits there. If I do this with 2 million, whatever this is, 20 million or whatever this is, you won't find it's going to do a significant nor. So it's like double the amount of time. I haven't actually got any more accuracy out of my answer. But you can kind of understand with this method, you can kind of go, well, because it's become stable at a certain point, you can say, well, these numbers aren't changing, whereas these numbers are. So this much of pi is correct. Without actually having to calculate at a high level of accuracy, it is relatively good at calculating accuracy levels. And that's an easy one. Pretty boring, pretty dull. We can do better than that. So I'm going to get rid of all this. I'm just going to cut them because I don't care. Right. So I thought the other way, or the really easy way of measuring pi, is to actually measure a circle. So you get a bit of string, you stretch it around a circle, then you stretch it out straight, and that tells you how long it is. The problem with bits of string is they stretch. And also drawing a circle is pretty difficult if you don't have other trigonometry functions, because if you don't have pi calculated, you probably can't do some of the other trig functions. So I thought, I saw someone online who had done something. I didn't watch their video, I didn't read their documents. You can do it with orbits, and you can calculate orbits. When you create spirographs, you usually use sine and cos to do it, but you can actually calculate orbits using complex numbers. And complex numbers in Python are one of my favourite things ever, because you can just pick them up and start using them without really any consideration for the complexity of the maths you're going to do with them. You just basically start using them. So I actually have a function here. I have another function here called draw loops. I'm going to bring that in, and I'm just going to use it in a second. So I'm going to make a data array to hold my data points in. Current point, I'm going to just set that to being at 1, 1, first of all. And I'm going to set my speed. I'm going to set the complex. I'm going to set my speed to being a complex of 1, 1 as well. And I'm just going to add these two together. So for I in range 10, just move 10 for the moment. Data.append current point. Actually, what I'm going to do is I'm just going to drop the current point in before that. Then in this range, I'm going to do current point is equal to speed. So it gets faster or slower depending on which way the acceleration is working. And so there's no acceleration rate, it's just moving at a constant speed, and then data.append current point. So I should get 11 because I should get 1 plus 10 more points than that. I'm going to do draw loops, and I'm going to do, it has to take an array, and you'll see why later. And you get a nice straight line moving from here to here. It's going 1 by 1 every single time. Pretty simple. But what I can now do is I can actually do acceleration. It's complex. I don't know, it's going to accelerate by 1 across every turn. Okay, and this time I can now say speed is equal to the acceleration. And if I draw that now, you'll see it begins every step, it's going faster, so the distance between the points is getting much higher because it's accelerating in a constant way. If you differentiate these points, you'll get a single point because of that's how it works. So nice and simple, pretty straightforward. Orbits, however, are a bit more fun than that, because with orbits, your acceleration is both variable but always to the center. So your acceleration inwards generally depends on your distance out, but also it depends on your the direction. So if you're over here, then the acceleration will be towards 0, 0. If you're up here, it'll be downwards. If you're down below, it'll be straight upwards. So when you start calculating this from the point of view of this is not a static acceleration. So instead now what we can do is we can actually say the acceleration, if we're going to make it more variable, is equal to, I want it to be inwards, so I'm going to say minus the current point, and it's going to be 1/10 of the value of the distance out. And I'm going to start by actually making it a little bit further out. I'm going to speed I'm going to make it move a little bit faster straight upwards. So it's going to start on the horizontal over here at 10. It's going to be going straight up at 5, and we'll just see what that looks like. And as you can see here, I'm only doing 10 points, but the 0 point is about here. And it's going round in a loop, quite far spaced out, but already we're going to get an orbit. So I increase this to 40, hopefully it will go around a couple of times, and straight away we're beginning to get what look like orbits come out of this system. So I'm going to decrease my size a little bit. But these aren't circular, but they are elliptical. And that's pretty awesome, that, like, straight away, without using trigonometry functions, we've just used pure math. And what's nice about it is that someone may go, they watched my earlier videos on fractals about how you multiply together. You might say, I'm using trig there because you're adding the angles together. Yeah, I'm actually not. If you want to multiply two complex numbers together, and this is really just the complex number of that naught. That's all that is. There is a very simple way of multiplying together, which means you don't do any trig whatsoever. It's just like almost like a quadratic. Just there's an equivalent, or you can do the point multiplication. So you're multiplying in parts of the original number times other bits. So there's no trig involved with this whatsoever, and you start getting these things out. The other thing is that I want to separate out loops, so I do want to start thinking of these as individual iterations going round. So the first thing I'm going to do is work out when it crosses the boundary. Okay, so I want to have this thing called the current loop. In fact, I'm going to get rid of data and just call it loops. So this is going to be an array of situations. Okay, the current loop is going to be an array of points. So loops is an array of loops. Current loop is an array of points. So I'm going to put the start point into the current loop. And what I'm going to do is, over here, it's where it goes from a negative imaginary number to a positive imaginary number. So I'm going to say if the current loop, in fact that should say not data there, but current loop. If the current loop, or the second from last place, dot imag, which is how you reference it in Python, is less than naught, and the current loop, actually it's the current point, which is the same as current loop, the last one, current point dot imag is greater than or equal to naught. That means we've actually gone across that border. What we're actually going to do is we're going to do the current loop, the -1 point of that is equal to the current loop, the start point. And there's a reason for that, is because basically they overlap. It's a bit hard to see here, but they actually go past each and overlap. So I want to say is if it goes past, ignore the last point and just join it up, so you actually get a bit of a circle going on. And now I want to append the current loop to the loops and then reset equals current point. So I'm going to start again with a new point as it is there. And that means that too many p's in append. That means you actually now have this concept of loops, where you get more than one loop going on. And I can also then say I want the first loop by saying that, and the last loop. So I can look at these loops very carefully like that. I actually need a close bracket there. Oh, because the IDs are a pain. There we go. Loops. So you just get the two circles on. And that's a basic orbit simulator done. Who needs Kerbal Space Program when you can do orbits like this? Not very realistic, of course. There's some issues there. Now, we want to encourage these orbits to become a little more circular. There's a couple of tricks we can do about that. First of all, instead of thinking about these as gravity, instead of thinking about where they're just attracted inwards, we can actually think about these as being attached to a spring. And the moment you introduce springs into things, pi is going to drop out, because springs, like perfect springs, perfect mathematical springs, not these stupid physics things, but perfect mathematical springs have a force heading towards its at-rest point. So if you put a mass on a spring and dangle it, the at-rest point is a certain distance. And if you move it away from that point, you can ignore if it crunches up or anything. If you move it away from that point, the force will be towards that point. So if you go above it, the force is the summation of gravity and everything else will be downwards. If you put that downwards, the summation of gravity plus the elastic force will be back upwards. So you can begin to imagine, instead of this force being always towards the middle, multiplied by 1/10, you can actually say it's a certain distance. So you can say if the absolute value of the current point is more, then it should be a force inwards. If the absolute value is less, then the force should be outwards. So I'm going to model that really quickly now. Okay, it's several minutes later. What is happening now is that the acceleration towards the middle, and the way I'm calculating towards the middle is this factor. This is a pointer at the middle. It's a pointer. It's a vector of unit 1 towards the middle, because I'm dividing the current point by the value of the current point, but by the angle of 0. So the angle doesn't change, but the value now becomes 1. So this is basically saying point at the middle from wherever you are on the page. Point at the middle. I've got a factor of 0.5 here. That factor will matter because that's how fast the acceleration we're in. And I also want to be this target away from my target distance. My target's currently 25. I'm just going to get rid of this and just put the first loop to begin with. And then I've also said this is the clever bit. It goes, but if the acceleration, i.e. the inwards, is less than 1, then I want to accelerate round. So if I'm in that sweet spot around the 25 section, in fact I can even do -1 like that, and that should be good. Then basically accelerate. And now this point here is basically saying multiply it by 0.5. Have I done this right? I possibly haven't done this right. So my acceleration inwards multiply by just a speed, basically. I've probably done this very wrong, but it's okay because it's all fun. It sort of works, and I'll show you it work in a second. But however, if it's more than that away, I don't actually want to slow down slightly. So if you're not in the sweet spot, I don't want you to accelerate, I want you to slow down, because I want you to come back. The acceleration inwards will be fast, you'll return to the sweet spot, and then as you enter that sweet spot, you'll accelerate around the curve again. But if you're inside that, or if your speed is going too slow, I don't need to be slowed down too much. So I just say just modify the acceleration. If your input variables aren't quite right, it does mean you'll just wobble inside the sweet spot, or just lock yourself in the sweet spot and you'll never get out. And then the rest is the same as it is. So if I just draw the first loop, you'll see you get a starfish effect going on, and that's not very good at all. In fact, that's pretty useless. But what's weird is, if I actually run it over time, is it actually begins to smooth itself out. So you can see here, this every loop I've done up to 50, it begins to get smoother. So if I just show the first and the last -1, first and last loop, you can see there is this distinct smoothing going on here. So the question is, can we calculate pi from this? And the answer is yes, but it won't be very good. But we'll show what that looks like. So to calculate pi from any one of these things is relatively straightforward. There's a couple of functions I've got already. Or what I want to know is the average distance from the centre to these points, which is just a matter of looping over every point and adding it up and then dividing by the number of points. And I also want to know the total distance. And the total distance for this is, because I've got 2 points, is the distance between the 2 points. And I have very handily put those into functions that I can just now call. And the functions are, I have lost them. They're in a thing called pi helpers. I made a handy pi helpers and then I lost it. So I'm going to go and edit this bit out now. Okay, so very quickly, what this can do is calculate loop stats, a quick little function. I've got a function called average radius and a function called loop length, which just calculates, as I said, the average radius, the absolute value, add them all up, divide by the number of points. The length is basically taking one point, take the next point, subtract them away from each other, and take the absolute value of what's remaining. That gives you the length going around the loop. And what you can do now is run it for a much larger number of loops, which is fantastic, and still take the same input and output. So we can run this, And then if I actually print len loops, you can see it's actually now got over 11,000, nearly 12,000 loops of iteration of time it's gone around the circle in this many points. So we look at the first one, look at the last one. We can also, if you really want to, throw in I don't know, loops 5,000, 4,000, whatever. You can see that it has actually become more stable as a circle going on. So as we now calculate pi, we call calc root stats, get my data from this, and look at the data. Again, here I can basically do take a few points if I want to. That is my last loop, and show that my pi value has come down to 3.36. Because it's wobbling in and out a little bit here, that's basically about as close I'm going to get with this simulation. Now I can change that, I can monkey around with these values. I can maybe change that to 0.4 and maybe change this one to 0.8 and this one to 0.8 as well. And you begin to see that you get radically different values are coming out at this point. Pi is going to be well out. My circleness is well out. In fact, this circliness shows me how much of a circle I've actually got. I definitely haven't got one. And my pi factor is out as a symptom of that. So yeah, it's a matter of playing with these values of what looks like a circle. Because I've got this factor which actually tells me how my circle actually is. This actually begins to give an answer of how the idea is if this circle becomes more circly, the difference in the minimum and the maximum comes down, it will slowly become more accurate pi. You could argue actually it would be an infinitely long if it went in and out, oscillated really, really tightly at 0.1 out. The circleness will be really high. Because of the way I've accelerated when it isn't accelerating in or out, that means it's very actually unlikely to do it. But this has become stable because my point at 4,000 is almost exactly the same shape. It's just phase shifting along very slightly between the two different iterations. So yeah, orbit simulation, it's not the best way of calculating pi. You really need to introduce what's called radial drag, which is what this thing here is trying to do. If I change that factor to 0.8, this is beginning to maybe this is the number which needs to be higher, because it's beginning to actually get a more accurate looking pi at this point. My circumference factor is coming right down. Maybe I change it into 1.2, and it's becoming less and less of a spirograph and more of a realistic pi. It's never going to come out as 3.1 using this sort of algorithm. But the main point I think I want to take away from this was complex numbers actually are really, really powerful, not just for theoretical maths, but for calculating where you want to have coordinates and doing physics calculations. They're really powerful for doing things like voltage and current calculations as well, doing phase differences, if you're doing any kind of RF calculations, even if you're just doing very simple oscillating circuits. They don't actually require a detailed knowledge of trigonometry. In this, I didn't do any sine, cos. There's no triangles in this. This is about the cleverest thing I did in there, just so the vector points in the right direction. And there's some tricks you can do to make your vector. I want a vector at 90 degrees to that, or at right angles, not at 90 degrees. There are various tricks you can use to do that. So yeah, that is basically it. This is my terrible pi answer of 3.39. No, I refuse to end on such a terrible value of pi. Instead, we're going to make some minor changes to this. The first thing is that I've changed my target distance out down a bit for reasons that will become apparent. My acceleration in needs to be around 0.1. It can even be a little bit lighter than that. Otherwise, if I have it too high, it bounces. The springiness is much too powerful. It needs to be much more gentle springiness, even possibly 0.05, although I'll leave it at this just for the moment. And then my acceleration here, I forgot I had to multiply this by 90 degrees, or if I want to slow down by minus, this is my radial drag and this is my radial acceleration. So if my point is here and my speed is my speed is in any direction, my velocity is in any direction, I want to accelerate it towards the actual circle. So this actually is always at 90 degrees to the vector going out. So the vector is out like that to here, then that will be at 90 degrees from it always. Without doing any more trigonometry or anything, that will always come out and it will come out incredibly accurately because complex number maths comes out much more accurate than doing trigonometry, which will get loads of decimal places wrong when you work it out. So multiplying by 0.02 just for speed, because I want to keep my speed down. When I run this, I end up with something which looks like this, which is wonderful. It is a very large orbit now, but you can see it is getting more and more circular. In fact, my circular stats now, if I run all the loops, you can see it's slowly getting bigger. But I run my circular stats now, my circleness factor is 0.01, and I'm not getting any real going in and out, so my pi is coming out at 3.12, which is 99% accurate. And the reason it's not going to get very much, it's not going to go above pi now, it's always going to be just below pi, is because I need another point. So the line between, say, this node and this node, there's another point here in the middle of it which will be further out. So if I could double the number of points here, it will get in. And the way you do that is by almost reducing this. If I reduce that by half, you find that your initial loop goes a bit weird, but you'll then circle at more points. This circle is much smaller than the first one was. And if I calculate that pi now, 3.13, I'm getting even more accurate. So my circles are getting much better, much more accurate. And again, I can tinker with these values. So I maybe change this one down to 0.1, this one down to 0.1, and this one down to 0.25. And you'll find that the circles are just becoming fractionally more accurate every time. It's getting closer and closer to pi. I'm within just over 2 thousandths out now of pi. 2 thousandths, it's 99.93 of pi, the value of pi, which I think is pretty good. I think for an orbit simulator, it's pretty good. The math is pretty good, and it's a much better than what I had before. And it was, as I said earlier in the video, I thought maybe I've done this wrong, and it was I hadn't multiplied to get the perpendicular angle. But I think that's pretty impressive. I think that's a win, and so I'm going to stop there. I'm definitely going to stop there. And if you liked this video, then please hit like, please hit subscribe. I realise it's quite a long one. I realise there was a lot of maths involved, but that's what Pi Day is. And I am going to go and hunt around the cupboard for some pie, and I'm going to eat it. That's it. Goodbye.